We're given a velocity function v of t equals negative 0.04 meters per second cubed times t squared. Now this needs to be a velocity. If we multiply meters per second squared by the square of the time, we're going to get units of distance over time cubed times time squared, which is going to give us distance over time, which is going to be a unit of velocity. And if we multiply meters per second squared by time, we're going to get units of distance over time once more, which is the unit of velocity. So the units are correct here, and they're consistent with the definition of velocity. Okay, so we want to find the net force on a 15 kilogram object at 10 seconds, assuming this is the velocity function for that object. So how do we do that? Well, we're going to multiply the mass times the acceleration. Now, the velocity is a function of time. Acceleration is going to be a function of time. So I write a of 10 seconds. This is function notation. The acceleration at 10 seconds. How do we get the acceleration function? Well, we take the derivative with respect to time of the velocity function. And we get negative 0.08 meters per second cubed times t and 0.6 meters per second squared. Very straightforward derivative. Plugging in t equals 10 seconds here, then we get the expression we see here. We've just put the 10 seconds in here. And when we multiply that out, we're going to end up with negative 0.8 meters per second squared and plus 0.6 meters per second squared, which is going to be negative 0.2 meters per second squared. Multiplying that by the 15 kilograms, we get negative 3 newtons. So that is going to be the force at the instant when the clock time is 10 seconds. And it's worth commenting that the velocity at 10 seconds is going to be positive. You plug in 10 seconds here, 10 seconds here, you find that the velocity, I think, is going to be 0.2 meters per second. So if that's the positive direction, the force is in the negative direction. So the force is opposed to the velocity. What's this tell us? This tells us that at this instant, the object is slowing down. And that's what's going to happen anytime the velocity and the acceleration are in opposite directions. The acceleration is negative. The velocity at 10 seconds is positive. Okay, so velocity at 10 seconds is plus, I said 0.2, it's 2 meters per second. So again, at 10 seconds, the velocity, the acceleration, and the net force. Acceleration and net force are both in the direction opposite the velocity. The object is experiencing a force opposed to its motion. It's slowing down. Now, another question asks, when v of t is 0, what's going to be the acceleration? When the velocity reaches 0, does that automatically mean the acceleration is 0? I mean, if you put zeros in for t, you're going to get 0, but of course you can't take the derivative of this function if you take one specific value of the variable. The derivative is always going to be 0 for any specific value of the variable. The derivative of the expression you get if you use a specific value of t, where you're always going to get some constant number, and its derivative will be 0. So you don't want to make that error. So at the instant the velocity is 0, and we can easily solve for that instant. We just set this expression equal to 0. We can factor out a t, so that t equals 0 is going to be a solution. And then what we get for the other term is going to be 0.04 meters per second cubed times t plus 0.6 meters per second squared. Setting that factor equal to 0, we find that v of t is going to be 0 when t is 15 seconds. We just divide the 0.6 meters per second squared by the 0.04 meters per second cubed, and we get 15 seconds. And you work out the details of that in order to see that. Then, if we want to see what the acceleration is going to be, we plug into our acceleration function a of t. Now that looks a lot like q of t, so let me make that a little prettier. Still looks a little bit like a q of t, but it's an a of t. And we plug 15 seconds into our acceleration function. Right here it is. When we plug in 15 seconds, this is going to become negative 1.2 meters per second squared. And this is still going to be 6 meters per second squared. So I think we're going to get negative 0.6 meters per second squared for the acceleration at the instant the velocity reaches 0. Now, that makes sense. The thing is slowing down at the 10-second mark, as we saw here, with the negative acceleration. And the acceleration is increasing linearly with t. The acceleration, as t gets bigger, you're multiplying it by a negative number. You're going to get a bigger negative number here, so the acceleration is going to be decreasing for t equals 10 seconds and for quite some time beyond. Matter of fact, for any time beyond. You can figure that out just by looking at it. Okay, so it makes sense that the acceleration would be greater and greater in the negative direction. Bigger acceleration, negative direction, more force in the negative direction as t continues to increase. So that when it stops, and it's just going to stop for an instant, it's going to stop and immediately begin moving in this direction faster and faster. There's going to be a lot of acceleration. And the reason I kind of pound on this point a little bit is when you have a pendulum moving back and forth, its acceleration is maximized at the ends of its oscillations, not at the middle. The acceleration is 0 in the middle, it's maximum at the ends of the half cycles. So there's kind of a connection here. So when you run into that a little bit later, when we analyze the motion of a pendulum, hopefully we won't be surprised by the fact that the acceleration is the maximum near the ends of the half cycles, near the maximum displacements from equilibrium. So I just added a note here. You get acceleration negative 0.6 meters per second squared at t equals 15 seconds. Net force negative 9 newtons. I think I might have said negative 6 earlier, but it's negative 9 newtons.